Should I repeat what I said earlier? Can't hurt to repeat it. This is section 3.5. Talks about the dimension of the four fundamental subspaces associated with the matrix. The column space is spanned by the columns of A. The row space is spanned by the rows of A. The null space is spanned by the solution set to AX equals 0, and the left null space, denoted N of A transpose, is spanned by the solution set to A transpose X equals 0. The basis of the column space is the set of pivot columns of A. The basis of the row space of A is the set of pivot rows of A, or the pivot rows of any row echelon form of A, including but not limited to RREF. The basis of the null space of A is a set of special solutions to AX equals 0, and the basis of the left null space of A is the set of special solutions to A transpose X equals 0. And A transpose X equals 0 is the same as X transpose A equals 0. That's why it's called the left null space, because the unknown variable is on the left of A. The dimension of the null space is equal to the number of columns minus the rank of a matrix, and the dimension of the left null space is equal to the number of rows minus the rank of the matrix. And no, I haven't done so. These are my professor's notes. I mean, I'm getting them through e-learning. I could post them. Yeah, yeah. Okay. Yeah, I'll post them. Yeah. Um, and another point that professor made was if you reduce a matrix A to an upper triangular form with a set of elementary row operations, you will get an REF of A, and the elimination matrix you use to get there. Let's call that M. Then the number of rows in the original matrix minus their rank. Let's call that S, for example. Then the last S rows of the elimination matrix will form a basis of the left null space. I need to process that myself. I'll come back to it. So this section introduces something called an LR decomposition, which is a generalized form of the LU decomposition, where LU decomposition really only works for square matrices. So LR factorization works for a wider range of matrices. L would be a lower triangular matrix, and R is any row echelon form of the original matrix. For example, this matrix A can be reduced to this matrix R using two elementary row operations, R2 minus R1 and R3 minus R2. Then the elimination matrix would look like this. So you have the multiplier corresponding to R2 minus R1 and the multiplier corresponding to R3 minus R2. And that's all for LR factorization. I think this can also model left null space. I'm not sure. No, it does not, because this is the inverse of the elimination matrix. this as an example. I think it's worth studying this example. The problem asks us to find a basis for each of the 4 fundamental spaces of this matrix, of the matrix result that results from this product, without computing the product of this matrix. The row space is okay. The row space of this matrix, of the matrix that results from the product of these matrices, is the same as the row space of this matrix, because this this matrix here is basically a elimination matrix. It is lower triangular, which means it can be formed from elementary row operations. And elementary row operations don't change the row space of a matrix. So applying any row operations on this matrix would preserve the row space. Therefore, the row space of this matrix is the same as the row space of this times this, which means the row space of this matrix would be just these two rows, 1, 2, 3, 4, and 0, 1, 2, 3. I think I skipped a few points. Is that clear? Okay. Column space. I'm not sure why the column space is just these 2 columns.
How many linear independent columns are there? You can see
2.
that.
Oh, the rank is 2. I'm not sure if multiplying these multiplying this matrix by this matrix changes anything but the column space.
I would think that it would, but maybe not.
Yeah, my professor said the column space would change if you reduce the matrix.
Oh, that's why it says L times column L of R. Because I think you
Oh, okay. L times
put it
column.
back.
Okay, yeah. Okay, that makes sense. Yeah. So multiplying this matrix by the first column and multiplying this matrix by the second column should preserve linear independence, which means they would still be part of the column space of the resultant of the product matrix. Because I don't think you're not swapping any columns. Yeah. It's okay. And the null space is found by just well, the null space of the product should be the same as the null space of this matrix, for the same reason as that for finding the row space. And so we can find the null space of the first matrix by setting the free columns, which are 3 and 4, equal to 1, 0, and 0, 1, and just solving some equations. You'll find that the null space is 1, negative 2, 1, 0, and 2, negative 3, 0, 1. I'm not sure what's going on here. You find a lower it looks like you're finding an LR decomposition for A. Oh no, you're given an LR decomposition of A. And you're going backwards. You're going from A equals LR to L inverse A equals R. You're finding L inverse and oh, this is the elimination matrix. L inverse is the elimination matrix, and you're finding just the last row because it's, if we go back up, you're looking at M minus R. R is the rank, I think. Yeah, R is the rank. M is the number of rows in the original matrix. So number of rows is 3. Rank is 2, because you have 2 pivot columns. So M minus R is 1. You're looking at the last row of the elimination matrix. That would be just this row, 6, negative 1, 1. And so that would be your only element in the basis of the left null space of A. Does anyone have any questions?
Finding left null space like that makes sense, but I feel like it'd be nice to practice it because I haven't used
Yeah,
that
definitely.
technique before.
Yeah, I don't think I've ever found a left null space. This is basically the same example, probably a little harder. Oh, okay. One more thing is, I remember when she was doing this example in class, the fact that you had to swap a row right here came into play later on. I don't remember exactly where.
It would definitely come up in writing out the answer, but I don't know where else it would appear. Oh, it would affect stuff like, wait. Yeah, if you were to find row space, you would just need to make sure to rearrange the columns of the row space. Or the rows of the
Columns?
row space, because by swapping rows, you could find an accurate,
Yeah.
yeah, you just need to remember to
Okay.
swap it.
Yeah. So so what that means is, if you find, for example, if you find this row and this row are, well, actually it doesn't matter. It shouldn't matter because you're not changing the rows. So you should be able to just extract the rows from the REF. You don't need to go back. Right? For example, if you find, well, we know you're swapping the row 3 and row 4, right? If you find after swapping that row 1 and row 3 are your only pivot rows, then if you go back here and say row 1 and row 3 are your pivot rows, it doesn't work because here you found row 3 is linearly dependent. So you're gonna have to remember that you switched rows 3 and 4. So row 4 and row 1 would be your pivot row. However, I think that logic is unnecessary because you should be able to just use the rows from here and here, since row operations preserve the row space.
You're right. It preserves the value of the row space, but the actual value you'll get back will have the rows swapped if you don't flip them back. Because if you think about it, if you say, row 2 is a combination of 1 of row 1 and 2 of row 3. But in the process of getting to that RREF, you swapped some of those rows. You'll get an accurate way to decode, to basically negate your free rows, but that row space or whatever will not match up with the normal. I think I'm also referring to the left null space, by the way. I may have been saying row space when I meant like left null space, so I apologize if that's.
Okay.
I believe it will matter at some point.
Yeah, I remember her saying it would matter.
I don't know if she wrote it down though. Here, do you know what day this was? I can see if I made a note of it in my notes.
Do you have the same professor?
Not Johnny, right?
Yeah.
Yep.
This was week 9.
I have it by calendar date. Do you know what chapter this is?
3.5.
Let me search real quick. This would be after vector spaces.
Yeah.
Da-da-da-da. It's 3.3, 3.4, 3.5. Okay. About how was this like the last thing we did in 3.5?
Yeah, except for like problem. Actually, no. It's not. We have theorems here.
Okay. Important method, which you I didn't write that down. Oh, I see. Okay. Hmm. Yeah, I think it's because when you did that when you do the method and you construct the matrix using the EROs, you have to remember that you did a row swap
Oh, okay,
for
okay. When you
the
go, oh, like right here.
for left null space. Oh,
Oh,
that
right
does
here.
look right. Yeah. Because the
Yeah.
0 column would be not at the bottom. It would be somewhere else. Because after you reduce it, you're going to have like the zeros on the bottom, right? But if you did a row swap, then theoretically, in the real matrix, that 0 row could be like row 2 as opposed to row 4. I think.
Well, why can't you just use a row swap for a row swap here?
I think you're supposed to. I don't know.
Yeah,
It made sense to me, but I don't know if I can explain it. Sorry.
it's fine. Anyway, let's just move on. There's another way to find the basis for the left null space, which is yeah, I don't know. Oh, okay. You perform the row operations on um on the original matrix, and you get until you get to the upper triangular form or some or whatever, or no, until just that row is zeros. For example, if you're going all the way to upper triangular, then you might have to go even further by swapping and then by eliminating some coefficients on this row or whatever. But if all you want to do is find just the coefficients corresponding to this row equal to 0, then you could go back into your elimination process, and as soon as you get a whole 0 row, you could stop and then write down a system of equations to find the left null space and set equal to 0. I'm not sure if that makes sense.
What are the EROs that they're doing in this section? Is this just the EROs to find REF?
Let's see. I think we went too far up. Okay. R2 minus 2R1, R4 minus 2R1,
Okay, so it's
R3
this
plus
example.
5R2. Yeah. So okay, you go until you find the 0 row.
Yeah.
That's as far as you want to go, because you don't care what these rows are. I think.
So negative 10R1, negative or 5R2, 1R3, 0R4. Oh, weird. Okay. And then that becomes a basis.
Yeah,
Wow.
these coefficients become your basis.
That's interesting. Okay. That's a
Yeah.
good thing to know. That can save a lot of time.
Is it the coefficients of that because of the L inverse matrix?
I think so. I think it's because of the L inverse. I don't know. I personally don't like this method. And finally, if you really wanted another way to do it, you could just take the transpose of A and find its null space using special solutions. These are just some examples. Okay. If you have two matrices, A and B, that can be multiplied together, then the column space of AB is a subset of the column space of A. That's weird. And the row space of AB is a subset of the row space of B. And the rank of AB is less than or equal to the minimum of the ranks of A and B. And now if you multiply a tall matrix by a long matrix, this matrix will if you multiply a tall matrix by a long matrix such that the product is a square matrix, the product should be non-invertible because the rank would be less than the number of rows. This whole proof for it.
Is that so? Were there any more? Oh.
Yeah, there's more.
Oh, yeah.
One more page.
Yeah, I was gonna say any. I thought it was like any m by n and n by m matrix together, but I was like,
Oh,
that
no.
doesn't sound right. No, it's only if they're both. They both got the dimensions. Wait, what? Let me read this again.
But yeah, m by n times n by m. It should be non-invertible, aka singular.
I can't remember the proof, but I'll take your word for it.
Yeah, that's the proof's over here. It's because let's see. It has to do with linear dependence and ranks. Okay. Okay, go ahead.
Oh, I was just gonna say, like, for that one, I think our TA said that is because if you multiplied it out, like all the values would be a linear combination of the other rows of the first one, or like
Yeah.
something like that.
So yeah, it was something related to that.
I feel like that would imply that it wouldn't be invertible though, right?
That's what. Yeah. Isn't that what I said?
Could
I said,
the matrix not wait,
I said non-invertible.
there's so many negatives. Okay.
Yeah.
So
If you
is
have
it or isn't it?
it is non-invertible.
Not invertible. Okay.
Yes, I think that's what I said originally.
Could the matrix not ever be invertible? Oh my god. Why did she write it down?
Wait, where?
It's in my notes. You must have written it
Okay.
in the annotated. Okay, so if
This
you
was the
ever
annotated.
multiply a tall by a long, it's not invertible.
Yeah.
Okay.
Yeah, right here. It is not invertible.
And
Okay.
that makes sense. That's where I was
Yeah.
confused.
If you have two matrices such that A times B is defined, then if B is invertible, the column space of AB is the column space of A, and the rank of AB is the rank of A. Proof is left as an exercise to the reader. If A is invertible, then the row space of AB equals the row space of B, and the rank of AB is the rank of B. That's comes from the definition of transposes, I'm guessing. That's basically it. I'm not sure if these last few theorems are necessary.
Which last two? Can you show me again?
These two, that the column space of a product is a subset of the column space of the first matrix, and the row space of a product is a subspace of the row space of the second matrix. And that
Yeah, these feel like things that you could probably
derive on the spot.
deduct, and they probably wouldn't be involved in the exam.
Yeah,
But yeah,
I think
I
it's too
guess
niche.
they'll probably show up again. Like she'll be like in chapter 7, she'll be like, "Hey, remember that conclusion we made?" or something. I don't think it'll be too relevant.
Yeah.
But understanding how it works can maybe help you get a better feel for how this kind of invertibility rank thing works for people who are having difficulty understanding it. Maybe. I don't know.
Okay. Any questions? Let's do problems. Okay, let's do problem 2, just the second matrix. From section 3.5. Let's take like 10 minutes.
Say question 2 from 3.5.
Yeah, just the second matrix.
Is there a PDF for that in the notes channel?
For the book?
Yeah.
Uh,
Or like the TA notes, or like where they solve it.
oh, for the problem?
Yeah.
I don't know.
Somebody was able to dig up answers to the textbook, but I don't know where they got them from.
They're from the publisher's website.
Okay.
But they only have the answers and not the actual solutions. Okay. Should we go over it?
Is anyone not done?
Okay. So we're given the matrix B. The first thing you want to do is get to reduced row echelon form, and these are the row operations I did on it. This is wrong. Right, this is wrong.
Your column space isn't correct.
Yep.
But you're close. You just need
Yeah.
to. There you go.
Yeah. So the first thing you do is get it to reduced row echelon form. You see that you have two pivot columns. Those corresponding columns in the original matrix B should be your pivot columns. And those they should form a basis of your column space. So the column space is spanned by 1, 2, and 2, 5. And these two are linearly independent, so they form a basis. And the dimension of the column space is 2 because you have two vectors in the column space. And now for row space, you have two linearly independent rows, and they span the row space. So 104 and 010 form a basis for the row space. Since the number of elements in the row space in the set is 2, it's the column space is the basis of the row space. Row space is 2. Making so many errors. Okay. For null space, I kind of did most of this in my head, but you want to set this row echelon form equal to 0. And then what you would get is that x1 plus 4x3 equals 0. x1 equals negative 4x3. And so and there would be no relationship between x2 and x3. You'd get negative 4, 0, 1. I'm sure I explained it poorly. I think if I were to write it out, I'd do a better job, but I didn't do it in the interest of time. Does anyone have any questions on how to find null space?
All you do is like,
Oh, go ahead.
I mean, isn't just like you set it equal to 0 and then you solve for the variable for.
Yeah, basically.
Yeah, I mean, I think we did a lot of
Very
examples
good.
on section 1. Like,
Uh,
well, without 0, but you know,
I think it was like 3.2.
yeah, 3.2. Oh yeah, 3.2.
Oh yeah, I was just gonna say, I don't have a question, but I found this video that really explained like how to find all 4 of the subspaces really easily, and it's almost like a shortcut way. I'm just gonna put it in. I think I've sent it before this video. It was just really useful. That's all I wanted to say.
Okay. I'll make sure to watch it later on. Yeah, and for null space, you have one set of, well, you have a set of one vector that spans the entire null space. A set of one vector is linearly independent, and since it spans the null space, this set is a basis for the null space. The dimension of the null space is 1. And finally, for the left null space, yeah. Yeah. Um, yeah, that's still a basis. No, that's still a basis. As long as it's just one of the, as long as it's just one vector. Yeah. If you had -401 and -802. No. I don't think you are, because it has to be one specific vector. Because the dimension of the null space, or the size of all linear combinations, right? Yeah, and for left null space, well, for left null space, the number of free columns, no, free rows and pivot rows, when added together, should equal the rank. The number of, or no, sorry, number of pivot rows plus the number of free rows equals the number of total rows. From the row space, we see that the number of pivot rows is 2. So the number of free rows should be 2 minus 2, which is 0. And the span of 0 vectors is just the 0 vector. So the dimension of that space will be 0.
Wish we could do an example that had like an extensive row space or a left null space, so we could
Yeah.
do.
Yeah.
In theory, there's ways to do it without having to
Yeah.
transpose.
Because that's such a long process. You don't want to do all of it.
But yeah, you
And
can
I'm not
literally
sure.
just do that.
Yeah, I'm not sure if you can take the I'm not sure if you can reuse the RAF.
No, you can't. You'd have to do the RREF again.
Yeah, you
which
have to
is
do
the
the
annoying
RAF
part.
all over again. Yeah. And then find the RAF. Yep.
Yeah. So you want to avoid that if you can. That's why they teach us a bunch of techniques to find row space and left null space without actually having to transpose it. It just,
Yeah.
if you do it manually, it just doubles the length of the problem.
But at the
doesn't-
end of the day, if you forget all the other ways to do it, that's a surefire way to get to find the left null space. Any questions?
So for the row space, well, for column space, I noticed that you use the original vector, right? You write like 1, 2, and 2, 5.
Yep.
For the row space, can you also do that? Like write the original, or
Yes,
is it
you
only the
can.
final? Okay.
You can, but well, yeah, you can because the row operations don't change the rows. You're keeping the original rows, except for instance, you can't do it with column space because you're changing the rows, not with null space. They're still or not with row space because they're still linear combinations of each other. But if you ever have to swap rows, keep in mind that if you go back into the original to the original matrix, and you use and try to say one of those swapped rows is a pivot row, you might run into problems.
So you use the not swap rows.
No, you should no. I mean, if you have to do it, I mean, you must do it. If you ever get a row of zeros, not at the bottom, then you're gonna have to swap rows. But you should remember that you should remember when going back up that you swapped rows. So if you find that your last row is a pivot row, but along the way from B to REF of B,
Mhm.
if you remember that you swapped rows 5 and 6,
Yeah.
and you get 6 as a pivot row,
Huh.
You should know that 5 is the actual pivot row, not 6, because 5
Oh,
is the pivot row.
okay. I see what you're saying. So there, you should always like check this the last one, because what if you swap rows and you forget?
Yeah,
Kind of see what you're
yeah,
saying. Yeah. Okay. Got it.
yeah. But I think it makes a difference in null space anyway, right?
Oh yeah, I think so.
I'm not exactly sure. I'd have to do one of those to see. Um, let's move on. Let's move on to another problem. Which one was that? That was 2? Yeah, that was 2. Let's do 4. This is this is a very good candidate for what we might see. Let's do problem 4.
Four. Section 3.5.
Yeah. How's everyone doing so far?
I think I have the answers, but I didn't work them out 100% just because I didn't think we'd have enough time.
Yeah. Should we take more time or just go over it? I'm not done, but I think I'm fairly close.
I'm ready to go whenever. Does anyone else want any more time?
Okay. I'm not too far.
Okay, see you one more time. Oh, okay.
I didn't get an answer for A, but for B, I got that it's not possible
Mhm.
because if the column space and null space are both equal to 1, their sum will be equal to 2. 2 is not equal to 3, which is a contradiction.
Yeah.
Therefore, it's not possible to have a matrix whose column space has one vector and null space is one vector. Wait, I skipped a lot of steps. Yeah, right. Same with null space. Yep. Yes. Yes. Well,
Did you find the dimensions? Because the dimensions are what's important. The
Yeah.
dimensions of what the matrix would have to be. Because the column space is that dimension, you know it's 3 rows. Because the null space is that, you know it's 3 columns. So if you know it's a rank 1 matrix and null space is effectively it would be the number of columns minus the rank. That's a contradiction because it's only dimension 1. Does that make sense?
Wait, did I do this? Is this correct?
It is correct. Right. Well, your conclusion was correct. Let me check your work.
Wait.
Dimensions. Yeah, that's right.
Equals
I'm
the
talking
number
about
of.
rank, but for this you don't need to find rank. You could just go based off a dimension of the column space.
Yeah. The dimension of the column space is equal to the rank.
Yeah, that's what I did, but they're equivalent, so it doesn't matter.
Yeah.
You got
Wait,
it correct.
is this correct?
Yes. So you
Uh,
could be more thorough and you can state because dimension of CA is 1, the rank is 1. Dimension of N is going to be equal to the number of columns minus the rank, which would be 2.
well, no.
But
Okay, yeah.
but you should show that the actual dimension is 1, which is a contradiction, and that's all
Yeah.
you need to show.
The
You just
3
need to
comes from the
prove that
number of
there's
rows, right?
what's up?
The 3 comes from the number of rows, right?
Columns.
Columns?
Yeah. Because think about it. When you're using
Oh.
because if you think about it, every dimension you have in your column space is a pivot column. Every dimension in your null space is a free column. So by looking at the null space, it's telling you there's 3 columns, but that it's also saying out of those 3 columns, there's 1 pivot and 1 free column. So there's a ghost column in there, which is a contradiction.
Yeah, okay. I got the right answer, the wrong reason. Okay, yeah, it's because the null space has well, it's a vector of size 3, right?
Yep.
And the null space to set any vector in the null space is a solution to ax equals 0. So a times what is it? 311 equals the 0 vector.
So it's a combination of columns. So the
Right.
number of digits will be the number of columns.
Here, I make this more
These
clear.
questions try and confuse you by needing you to kind of keep track of the rank, the size of the matrix.
Yep.
Yes.
Yeah, here it is. A times this vector must equal to 0 vector, which means A has 3 columns, because the number of columns in A must equal the number of rows in this vector for multiplication to be defined.
Let's go back to 1 because
I
uh,
didn't get it.
so the trick is you could probably do it 2 ways. One way would be the very rigorous setting up, A, B, C, D, E, F. But with this example, you could cheat a little. What I did was I set the columns equal to the number of columns because I recognized that would be a 2 by 3. Then I used basically backwards EROs to show that you could arrange the row space to work that way. Because like we said, EROs do affect they affect the column space, but they don't affect the row space. So by going backwards, I was basically starting with reduced, or I was starting with REF, and I was going to, what am I saying? To the normal version of it.
Yeah.
So
I know what
I
you're saying.
ended up with 1, 0, 1, 2, 2, 5, which does satisfy it.
Does it?
I think so.
Wait, what'd you say? 1, 0?
1, 2, 2, 5.
I put 1, 2, 1, 2, 2, 5.
I'm not sure that works. Uh, okay, what is it? 1, 0? These are rows, right? 1, 0, 1, 2?
Yeah, 2, 5.
I don't think this has the column space 1, 1, 0, 0, 0, 1. Because you can't, because
Yeah, I made a mistake.
anytime you subtract 1 from the 2, you must also subtract a 1 from the 0 as well.
Disregard my answer then.
I think 1, 2, 1, 2, 2, 5 will work.
The thing I don't understand is I thought the column space was supposed to be the pivot columns of like the non-reduced version.
Right. Yeah, but all linear combinations of them. It says contains, not a basis, not a basis for. So yeah, this is tricky. I think this matrix might work, but does this have column space 1, 1, 0, 0, 0, 1?
It objectively doesn't. I think my process may have been onto something. I just had a brain fart. I think what you could do is you could start with the row space and then try and reduce it to the column space. That would work because the EROs would not affect the row space, but it could let you get to the column space. I don't know that. You could always do it rigorously and just make an equation.
I don't know. This is 4. Yeah, 1, 1. What?
Yeah, I think that's actually right. Because you just need to prove. So, like I was saying, if you start with this and then you can show that you can get to the row space through EROs, then you're golden. So, what you would start with this, show that you can get to that row space combination, and then you're good.
I see. Yeah.
So, I did it like backwards.
Yeah. Okay. And then for part C, I got exactly what they got. I just got a matrix, a 2 by 1 by 2 matrix, with one free column, and this has it has a null space of 1. A null space of dimension. The dimension of the null space is 1, because you have exactly one free column. Dimension of the left null space is 0, because you have exactly 0 free rows. I didn't get this one. I was close. I would have gotten. I was on to something.
For which one?
For C, I would have gotten this. Except I would have divided by 3. I would have had fractions.
D. Oh, I showed that it was possible, but I forgot to actually construct it.
Yeah, I was. My answer would have been 3, -1, 1, -1/3. But basically, the way you get it is because, well, first of all, it's possible because the rank is 1, and you have 2 columns and 2 rows, and one of the columns is just the other times -3, and one of the columns is a multiple of 3, 1. So you have 3, 1 as one of your columns, and a multiple of 3, 1 on your for the other. The other multiple would be 3, 1 times -1/3, or divided by -1/3, and that would have given you negative 3, 1 and -1, -1/3. The textbook decided to multiply that by 3 to avoid fractions, and they got 3 or 9, -3, 3, -1.
Look at their answer to E.
E.
Check the next section for how to prove this.
Yeah. I mean, I was gonna say, I was gonna do the exact same thing. I was gonna say orthogonal complements.
Yeah, I wasn't even thinking about that. I guessed yes, because I thought that maybe you could just extend the number of free columns, but I forgot that it said row space equals column space, not same dimension. So that makes sense.
What is it? What is it saying?
So if row space and column space are the same, that means it's a square matrix because the
Right. Yeah.
dimensions.
I got that.
But as a result, using the same formula as we used earlier, we know that the dimensions of null space and left null space are the same. But what they're then saying is that, wait, what?
Yeah. What they're saying is orthogonal complements.
So
The null space is an orthogonal complement to the row space. The left, or no, the null space is an orthogonal complement to the row
Did
space, and the
two
left null space
things
is an
be
orthogonal complement.
orthogonal to the same thing but not overlap? I Ooh, that's a little spicy. I don't know how we would prove that without.
Yeah, no. The definition of two vector spaces being orthogonal to each other is that every vector in the first one is orthogonal to every vector in the other, which means no vector belongs to both spaces.
Yes, but it's saying that NA and NAT are orthogonal to the same identical space. Here, those are the same space. But I don't know why they're saying here those are the same space. And maybe that's the only way they can be, is for them to be overlapping. This example is not going to be on the test. This
Yeah.
is definitely some weird shit.
4E will not be on the test. Yeah.
Did anyone figure out E? No? Okay. Yeah, that's a little weird. I think at some point, once we get more comfortable manipulating like orthogonal spaces, it makes more sense. Or maybe we just missed something, but
Yeah.
I just assumed the m minus r has to equal n minus r thing, but I don't know how you would prove that it's a square matrix.
Well, that just comes from the fact that the row space and the column space. Well, if the row space and the column space are the same, then they're both subspaces of the same. You know, if they're both subspaces of r squared or of r cubed or r to the fourth or whatever.
that's a good
Not.
point.
Yeah, that's how I did it. I said the null space. Well, it means that the number of rows is the same as the number of columns, because the nu- the n- the null space is, oh sorry, the column space is a subset of r to the uh, m, and the row space is a subspace of r to the n. And if the row space and column space are equal, then m equals n.
So column space tells you how many rows there are, null space tells you how many columns there are. So if they're both the same, then you know it's a square matrix.
Yeah.
Yeah, I was thinking of it in terms of different columns, so that's why I got a little confused.
Okay.
I'd be down for maybe one more, but I kind of want to wrap up soon.
Yeah, me too. Um.
Oh, and I asked my TA about the polynomial problem we were going over yesterday,
Oh,
and
okay.
he didn't. He wasn't willing to prove it in the rigorous way. He just kind of started with the answer, and I almost like basically for like 20 minutes was like, how can I convince you to show your work? And he just wouldn't. So
Proof is left as an exercise to the reader.
yeah, but I think we should just memorize that case about how it works, because it's the same if it's like polynomial equals 3, polynomial equals 4. It'll be the same solution. You just want to, I guess you just start with the answer and prove that it's correct. But yeah, I don't know. I don't want to think about it anymore. So
17 looks good. Or no, not 17. 14 looks good. I'm trying to see if there's better one that's more worth our time.
that's another one with no left null space.
Is it?
Yeah,
Yeah, it
Wait.
is.
rank 3,
Useless.
3 rows. Yeah, let's find a beefy. Oh wait, let's see. Wait, what is 19? Reduce A to row echelon and look at 0 rows. That's. I think it's easier for them to print fat matrices rather than tall matrices, so there's not a lot of problems with left
Yeah.
space. Embarrassing.
Wait. There is no 27. Or there is no 35, is there? Oh, I was looking at the wrong section.
Yeah, it's 3.5 for the one we were talking about yesterday. Wait, I guess it's 3.4. I don't know what you're talking about.
Yeah, let's just do 14, I guess. Or wait, maybe if to find null space, there might be an example in the in a previous section. A left null space. I mean, I think they introduced left null space earlier, but we just didn't cover them until 3.5.
Three 3.5 is where they introduced the concept of the 4 subspaces. So
Um, yeah, let's just do 14.
Okay.
Let's take like 5 minutes.
Which problem again?
14. Okay, should we go over it, or should we take more time?
Just finished. Is anyone else working on it?
I'm not done myself, but I'm close. I mean, I'm pretty close.
Ah.
Let's just go
Column
over it.
space took a minute. All right.
Column space took a minute.
Bad at matrix multiplication.
You're not. Okay, yeah, yeah,
Got to do it for the columns,
yep.
I think. Yes,
Yeah,
vector multiplication.
I wasn't able to find the null space, but for column space, you know that the columns shouldn't change at all. So
Huh?
the columns, well, the columns will change, but they won't. Okay, I know what I'm saying. Okay, the column space of A is the column space of no, it's column space of A is L times the pivot columns of the second matrix, where L is the first matrix, which would be just 100610981 times each of the pivot columns, and the pivot columns are the first three columns. So you just multiply the matrix L with these three columns, and this is what you should get. Is that correct?
No, not quite.
What'd you get?
I got 169,
Yep.
2, 13, 26, and then the last one was the same as yours.
Really? I got 320, 29.
Oh, okay, I see what I'm doing. Okay.
Might be multiplying it by like the whole matrix or something. Cause round? I don't know. Is that how you
Okay.
do it?
I know what I'm doing wrong. Yeah, should be 1, 6, 9.
The first one won't change. Well, it'll be exactly equal to that because it's just a 1.
And then 2. Is this correct?
Still not what I got. Well, your
Mm,
first one
Still
is.
0 is
What?
different from mine because I got 2, 13, 26.
I got 2,
26.
14, 26, but 13 could be right too. Change my answer to that. Then I got 3, 20, 29.
326. 3, 20, 29.
Moral of the stories are all bad at math.
Yes.
Bad at arithmetic. Let me calculate that last column again. That'll be 3 up top.
Yeah. I think the last one is 44 because it's 27 plus 16 plus 1, which is 27 plus 17, which is 44.
Good.
I think this. I'm pretty sure this is correct.
44. Yeah.
Yeah. And for row space, the first one doesn't. The first matrix doesn't really change the second matrix because you're performing row operations and not column operations. So,
You don't have to change anything. You just grab all the rows.
yeah,
Rank 3.
yeah, yeah, yeah. You grab all the pivot rows, which happen to be all the rows in the matrix. So it's gonna be 1, 2, 3, 4.
It's rank
0,
3
1, 2,
with
3,
3 rows, so you know that the left null space is just the 0 vector.
0. Right.
Make sure to include the 0 vector.
Well, no, you don't say the span of the 0 vector. If you're writing it as a span, it would be just an empty set. The basis would be an empty set because the dimension's 0.
Yeah, that's. You're welcome to try it on the exam, but every time she does it in class and every time my instructor does it, they make sure to include the 0. It's always in there. And to be honest, the dimension of the 0 vector is of note too, but usually they just write 0 vector. So it's
I
up
think
to you.
I don't want to argue too much, but the
I
0
do know
vector is the
factually the
equivalent.
basis of it. If it's dimension 0, is 0 vector, which is what we're trying to find. You're writing span, which shows that you know what you're going for, but like I believe they're asking for a basis, right?
Yeah, and the basis would be the empty set, wouldn't it?
No, it's not. The basis is the 0 vector. Let's Google it. They may be teaching it weirdly in class, but
Let's just find the answer. 14 empty basis, so it'd be an empty set.
A vector space that is composed of just the 0 vector is 0-dimensional, and its basis is the empty set.
Yeah, that makes sense. Because okay, this the null space, the left null space is equal to the span of the empty set, but the set notation for the actual null space is the 0 vector.
Can you say that again?
These two are equivalent. Saying the span of the span of an empty set is equal to the set containing only the 0 vector, and the basis of this vector space would be all linear combinations of nothing, because the zero vector is trivially present.
Oh, I see what it is. The null space is still the 0 vector, but there is no basis.
Right.
Okay.
Because the null space, because the 0 vector is trivially present.
Yes. Okay, we're good.
Yeah, I didn't find the null space. I know how, but it's just
Null space is kind of easy because you don't actually have to do the combinations. You just go based off of. You can go based off of the REF. So I just made combinations that made the free column. You negated it. So I got 0, 1, -2, 1. So I just found a combination of the other rows that made the free column 0.
wouldn't you find the REF?
That is an REF.
REF.
You don't need to. You just need to show the rows. And this shows it. It shows that the first 3 rows are what's it called? Pivots, and the last one is a free column, and you can
Right.
see just based off of this that you can make that combination. The combinations do stay the same. Even though like the bases change, like you couldn't grab the columns from the REF, they still combine in the same way because you're using EROs.
Wait.
So
What combination?
so the combination would be if I had 0 of the first row, 1 of the second row, -2 of the second row, that would be equal to negative the last. I'm saying row. I hate this. This is so annoying. It's not, math is not meant to be spoken. Just take if you
Wait.
I mean just add it. Take column 2. Take -2 times column 3. And then take 1 of column 4, and that's 0. And that will be the same for the actual column space. You can figure it out. You got it. It's in the notes. Does that make sense?
Kind of.
It's the exact same way you would do it normally. It doesn't change here. You just treat this as though it's REF.
I just did like a back substitution.
Back
Okay.
substitution.
I mean,
Uh,
I guess there's multiple ways to do it, but I think the main point they're trying to make with this problem is that you completely ignore the left matrix, right?
For the null space, you don't need to know the left matrix. That is correct.
Right. So I mean, regardless of how you do it, as long as you're using only the last matrix, should be fine.
Yes, the combination that makes it null doesn't care about the EROs you use.
Right.
So the only thing you need the left matrix for is getting the CA, because the CA does care about the
Well, and the left null space, but since it's empty.
yeah, doesn't matter here. Okay. Cool.
Yep. That should be enough, in theory.
Yeah, I need to work on LD stuff.
Yep, I do too.
Because I missed that one. I'll be doing that tomorrow at the library. I'll probably find some people who want to go over it. Did we ever get answers to last year's exam? I mean, do we
I don't
have
know.
2 copies of last year's exam like we did for the previous exam, or just the one?
I have no clue.
All right.
Okay. Well, it was nice studying with you guys.
Thanks for putting this on.
yeah, thank you.
Good luck to everyone. I'm sure we'll all need it.